Claudio Calosi, who many of you know, who is assistant professor at the University of Geneva and principal investigator on the SNF funded project, Metaphysics of Quantum Objects. We're really happy to have him here on his birthday, no less.
There you go.
And he will be speaking to us about making determinable indeterminacy precise. Take it away, Claudio.
Okay, so first of all, let me thank again and again Amanda and David for having me, because as I was saying, I've been asked to write this thing for a special issue, and I was between lazy and late, or well, let's say at the union of lazy and late, not at the intersection. So I didn't have any time to actually discuss with everyone, and I'm very happy that there is a very good. I know that there's a very good logician here, Bruno. So if my logic is bad, just please tell me so that I'll make a fool out of myself. And so, yeah, and once again, this was, so I was asked to say something about the logic of a particular account of indeterminacy. And that's what this is about. So in general, of course, it's about indeterminacy, let's say. And under this umbrella term, I mean, there's many phenomena that goes on, right? I mean, some people believe that indeterminacy can help us actually make sense of the openness of future. The difference between past and the future is the past is determined and settled, whereas the future is open and indeterminate. Some people think that indeterminacy is at the core of what we usually call Scarlet cases. So the most famous of which probably is the paradox of the heap. Now, let me apologize to Amanda, because all the beautiful quotes that I have, she already saw them. I'm sorry, I just couldn't. Anyway, so I'm saying this just because I think, wait, can you see that? Did you see this? So, okay, so this is, so I'm insisting on the paradox of the heap because I think that this is going on in the first actually page of my favorite play of the last century, Endgame by Samuel Beckett. This is the very first thing that gets said in the play, and there's Clove that's in his kitchen, right? And I think it's actually, so we know that Beckett was reading philosophy at that time. So I think this is exactly the paradox of the heap, as a matter of fact. So here's the paradox that says, well, a grain of sand does not constitute a heap. Adding a grain of sand to something that it's not a heap cannot actually turn something that's not a heap into a heap, because this is just an unsubstantial change. But of course, if you repeat the argument, you end up with all the grains of sand in the shore of the Atlantic Ocean, which do not constitute a heap. And I think that Clove actually knows that very well, because it says there's a heap, there's a little heap, and then that's the impossible heap, right? I think this is so given that I'm so to me, Samuel Beckett's like the Backstreet Boys for someone. I'm just a fan. So I always wanted to put this quote before we started. But this is not actually the case. And so what I'm going to propose is I'm going to take a deep dive into one account of indeterminacy. Now, it's a huge question whether the account that I'm about to go into actually can fit all of these different things. The future case, the heap case, another case that I'm particularly interested in is the quantum mechanical case, and so on and so forth. Now, I tend to think that it can't, as a matter of fact, but I know people that want this account to rule them all. Like, oh, this account is enough to actually deal with all the cases of indeterminacy. And it's in a particular indeterminacy that we're talking about. It's metaphysical indeterminacy, that is indeterminacy in the world. It's not indeterminacy because we are using a semantically defective language, or it's not indeterminacy due to our ignorance, okay? So this is the outline, which is very simple. So I'm going to introduce you to this particular account, which is called the determinable base account. And it crucially depends on the distinction between determinable and determinate's properties and the relation between them, that it's called determination, okay? So I'm going to give you a formal construction to capture that, which pays particular attention to what we will call intermediate levels of determination. So you're going to see there's going to be a top level, a bottom level. What happens if there are levels in between, okay? I'm not going to argue that they're metaphysically significant. There are arguments in the literature. I'm just going to ask, oh, if we do admit that there are more than two levels, right, what does it happen? And in particular, what does it happen for the determinable base account? And I will show you, I will tell you that there's, in the literature, only two cases are considered. It's called Glappi and Glatti. You will see what it means. And I think already at this stage, the introduction of intermediate levels of determination is important. You will see the consequence that it has. But even most importantly, I think, more significantly, it opens the way for a third way of something being metaphysically indeterminate, which I'll call Glappi for, lack of imagination, I would say. And in the conclusion, there's going to be another beautiful quote. So you can sleep from 1 to 5, but just wake up at 6. Okay, good. So here's what the determinable-based account says. There is metaphysical indeterminacy when there is an indeterminate state of affairs. It is a state of affairs which has a constituent object X, which has a determinable property, but fails to have a unique determinate of that determinable. And we'll see what it means, okay? Now, I'm gonna abuse terminology here and say sometimes that X itself is indeterminate, okay? But the letter of the account, which is due to Jessica Wilson, actually has it that it's the state of affairs constructed out of the object that is indeterminate. And usually there are two ways in which one thing might have a determinable, but no unique determinate. Either it has no determinate, which Jessica calls Gappiani, or has more than one. We will see, albeit in mediated fashion, which Jessica calls Glattiani. At this point, I should also mention that I've done some work with Jessica herself on quantum indeterminacy, and what I'm about to say is she finds it problematic. So it's only me. So just to make things clear. Okay, good. Usually, determinables and determinates are constructed as relative to levels of determination. So the usual example that we all go for is, okay, take red, right? This is a determinate of color. So the red is more specific, more determinate than color, but is a determinable of, let's say, scarlet, okay? So usually, if a property counts as determinable or determinate, is relative to levels. One property might count as determinable and determinate, relative to different levels or relative to different properties. Now, the gist of the paper is actually to analyze what happens if you will see there's a top and the bottom if there are levels in between. The color case might be the paradigmatic example. So you have color, you have red, you have scarlet. So the red level, right, it's in between the bottom and the top. And in particular, I'm going to explore the consequences for the DBA I'm introducing now. Okay, so now we're going to go to that. So the first thing that I'm going to do is provide a formal construction that is able to capture some of the features that we wanted to capture. And so my hope is that I did that. It works. I think there's a serious limitation. I think it works only for discrete structures, for example, as it stands. But I hope that it works, and it works just with having only one primitive notion. Now, that's my hope. It might very well be that I'm completely off. So please tell me. I don't take these things personally. So just tell me that. Okay. So, but here's the introduction, right, to determinants. So determinables are, in first instance, type level properties that stand in a distinctive specification relation, the determination relation. So as I said, color, then you have red, then you have crimson or scarlet, and so on and so forth, okay? So all the quotes will be taken from the introduction, the SEP introduction written by Jessica herself. And usually, as it's the case in many theories of particular relations, such as the relation of determination, the relation is characterized by a bunch of principles, okay? So I don't remember how many Jessica lists, but let's say there are, a lot, and some are more central than others. And as far as I know, there is no classic axiomatization, like there is a classic axiomatization of, I don't know, standard mereology. So we don't know, for example, I mean, it's pretty obvious for some, we don't know which are logically independent or not, which is the minimal set of axioms that will generate the structure. This work still needs to be done, at least at a certain level of generality. My focus will be on two principles, actually a little bit more, but these will be really center stage because these will be violated by cases of metaphysical indeterminacy. That's why they're so central. The first one is requisite determination. So this is just Jessica wording. I'm going to tell you, so requisite determination basically says that if you have a determinable then you have a determinate. That is to say, if you are colored, then you're either red or blue or green or whatever. Okay. Unique determination, like, says that if you have a determinable and a determinate at a certain level, then you have only one. It just says, oh well, if you're colored, then let's say you're red. Well, if you're red, right, you cannot be both red and green at the same time all over. And let's say if you go down a level, if you are scarlet, you cannot be both scarlet and crimson. Something like this, okay? And you can see here that it's written like for every level, right? It seems a quantified statement of for that level. And it's going to be important. Okay. So as I said, right, usually you say that determinables admit of different levels of determination. Now, it might very well be that some cases only admit of two. So for example, David Lewis thought that masses admits only of two. You have mass and you have a particular value for the mass, and that's it. So you have just one top level, the bottom level, there's nothing in between them. Now, all this project actually makes sense if and only if there are levels in between. Otherwise, you know, everything falls apart. And the first thing that I'm going to do is I'm going to try to capture everything that I can with just one primitive relation, which is going to be D, the determination relation. Now, these are, I don't think I need all these assumptions. I think actually I can derive some, but just to be safe, I just put them all on there. Say, D is my primitive relation, which I will assume is a strict order. And I will assume, I don't think I need to assume that as a matter of fact, but that it holds between levels. That is, if D holds between these two properties, D stands for determinable, you will see what the superscript stands for. Then these two things are at different levels. Okay, so so the relation of determination can only hold between red and scarlet. It cannot hold between red, let's say, and green, because that at the same level, or color and red. So then I'm going to argue, then I'm going to assume that there is a top level, a level such that there is no level such that things that inhabit, stay at this level are determinable of that, and there's a bottom level. So the top level, so the properties at the bottom, at the top level, are what we call maximally unspecific determinables. They are determinables that are not determinate of anything else. Okay, there's no D relation that goes first. First the one at the top and then another thing. And the bottom level is the maximally specific determinate. So you cannot get any more determinate than that. Okay. So formally, there is nothing such that the relation D holds between property here, okay, and another property in that order. And now for the more so this is one controversial one, I think. Not sure, but there's only one property at the top level, but there are multiple ones at the bottom level. As a matter of fact, this is required in most of theories of determinables and determinates for all the levels beside the top. But there has to be at least two, as a matter of fact. And then I will say that DIN is a determinable of that if the D relation holds in this order. So the only thing that you need to remind here is that, so the first argument of the D relation is the determinate, is the more specific one, okay? That's the only thing that you need. So in that case, you will have the relation holds between scarlet and red in this order. And we will say that scarlet is a determinate of red, conversely, red is a determinate of scarlet. And as you can see here, it just swapped places, okay? Good. So, first notion that I'm gonna define is immediate determination. So this is I mean, I know that's a lot to take just if you never see these things. So here's how to think about it. This is just successor of, right? It's just the same thing, right? Like 3 is the successor of 2 because it comes after 2 and there's nothing in between them, right? I mean, there's no natural number in between them. Something is, a property is an immediate determinant of the other if the determination relation holds. And intuitively, that's what this conjunct is saying. Intuitively, there is nothing D-related in between, okay? So suppose that you have color and then you think that red, blue, green are the immediate determinants. That means that you don't think that between color and red, there is anything here. So you pass directly from red, from color to red, and then from red to scarlet, let's say. Good. So the target notion that I want to define, and that's crucial for me, is I want to define the notion of a property being at n steps from the top level. And I'm going to do it by induction. So here's how I'll write this. So a property is one step away or n steps away from the top level. Okay. So first I define the base case, right? Is one step away from the top level. It just means that it's an immediate determinate of the top level. Okay. So, and if you plug in the definition of immediate determination, you will see that just means that there is nothing in between, right? The top level and the first level. Okay. So now now I'm going to define the target notion by induction and say, well, a property is n steps away from the top level if there is a property which is n minus 1 steps away from the top level, and the property I'm interested in is a determinate of that, is an immediate determinate of that. Okay. So that's the Baroque construction that, as far as I can see, work for discrete structures. Once you have discrete structures, you can, I think, I didn't check it, but I think you can actually define a metric on this set, and you just take the distance between two properties to be the absolute value of the difference of steps, and then you can just define immediate determination and all of that in those terms. But I didn't check, as a matter of fact. That's an open question. So good. So why did I do that? So first a remark about the construction. The remark about the construction is that when immediate determination holds, it always holds between a property that's at n minus 1 level, and so at n minus 1 steps from the top level, and n steps from the top level in the reverse order, right? So you got the n steps, n minus 1. Okay. In general, due to the transitivity of D, because I assume that, and of ED, which you can prove, if a determination relation holds between two properties, the first one, okay, the first argument is going to be farther away from the top level, okay, than the second argument. That's going to be crucial. Okay, good. Am I making myself clear? That's the first time I'm presenting this, so good. Okay, why am I doing all this incredibly boring stuff? Well, I'm going to use it. I'm going to use now this machinery to define two relations. The relation between properties, as you can see here. The properties of this is the relation of being more steps away from the top level, or being farther away, or being at a greater distance. Okay, and this is the relation of being at the same steps away from the top level. And it just says, well, what does it mean for a property to be farther away from the top level? Well, it just means that there's a level. This is an SI. So, oh yeah, I forgot to mention that. I will call properties that are one step away from the top level S1 property, properties that are 2 steps away S2 properties, and so on and so forth. So this means that the first one is a SI property, the second is a SJ property, and I is just greater than J. It's just you have to take more steps. It's not right to get to the more specific one, right? To get to Scarlet, let's say, you have to walk more than to get to red. And instead, on the relation of being at the same distance, right? It's just you have to take the same number of steps. So, for example, green and red, right, are at the same distance. Why? Because you only have to take one step from color. And I think Pervincol and Scarlet are at the same level. Why? Because you have to take 2 steps. You have to go from color to red, from red to Scarlet, and from color to blue, and from blue to Pervincol. I think it's well, whatever. Let's assume that Pervincol is a shade of blue. Good. So clearly, this just upon inspection, relation number 5 is an equivalence relation. So what I will do is that I will take levels of determination to be its equivalence classes. intuitively, what they are is they're, let's say, union. If you just set theoretic, so if you use set theory just unashamedly, there will be unions of properties that sets containing properties at the same steps. They are the same steps from the top level. So in the case of color, there will be green, red, blue, blah, blah, blah. Or level 2 will be scarlet, crimson, maroon, periwinkle, ultra, whatever, sapphire. Okay. And of course, the equivalence classes will induce a partition. That is, well, this will ensure that every property belongs to only one level. And the union of the levels will give me the entire family of properties. If I take the union of all the levels, I will get scarlet, crimson, blah, 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 red, green, blue, blah, 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 and color, okay? Okay, so now, so the crucial notion in the literature on determinable determinants is a level is more specific than another, which, you know, is more specific. Clearly, it's supposed to be a strict order, right? Now, I am going to define a strict order here. Like, so level I is more specific than level J if the properties belonging to the first one are more steps away from the top level than the second ones. So why scarlet is more specific than red? Why the level in which scarlet lives, let's say, is more specific than the level where red lives? Well, because you have to take more steps to get to scarlet from the top level than you have to take to get to red. Okay, and the same thing goes just for properties. Now, if you remember, I started with, oh, there's D, which is a strict order, right? And now I just defined another. Now, the first one is a partial order, right? So not every two properties are related by D. So for example, periwinkle and red, they're not related by D. Periwinkle is a determinate of blue, not of red. On the levels, I think it should be a strict order, okay? A total order, sorry, a total strict order. Now, what you have to check is that these orders are consistent, I think. So that is, look, so you have an order induced by the D relation that says, oh, let's say crimson is here, right? And red is here, right? So this is the order induced by D. And now you have an order induced by this guy here that says, oh, this level is more specific than this level. And you have to show that they match, right? Because it will be tragic for the construction if you have, oh, you know, one order goes in one direction, therefore crimson is more specific than red, but then my definition entails that, you know, the level at which crimson lives is now less specific than the levels at which red lives. So I think it's enough to prove 8 and 9. 8 and 9 should give me that the orders are consistent. You don't get that D goes in one direction and minor, let's say, goes in the other direction. They go parallel, which is exactly what you want. So here's the claim, right? A for determination relation holds between these two properties. Oh, and I use superscript. So you can see here, the superscript actually indicates the level at which they belong, which actually counts the steps. Okay. So why does these, so it says, well, if a determination relation holds, let's say, oh, if scarlet is a determinate of red, then the level at which scarlet lives is more specific than the levels at which red lives. Now, and I think I can show this roughly as follows. So you remember that deconstruction has it that whenever these things hold, this thing here is farther away from the top level than this. And if it's farther away from the top level, definition 6 entails that this level is more specific, which is exactly what you want. And once you have 8, it's easy enough to get 9. 9 says, well, if something is more specific, if a level is more specific, right? So suppose that the level at which crimson lives and scarlet lives, so they live all the same level, right? Is more specific than where red and green and blue live. There is no determinate such that the one that lives at the more specific level here actually is a determinable, okay, of the one that lives here. Okay, so that's what it says. So now, and once you have this is almost straightforward, right? So suppose that's not the case, right? Just by reductio. So suppose you have the antecedent, Li is more specific than Lj, but you have the negation of this. Therefore, you have two determinate, one that lives in Lj, one that lives in Li, such that this relation holds. D goes from Dj to Di. If the relation goes from Dj to Di, 8 entails that Lj is more specific than Li. But we just assume that Li was more specific, therefore this will violate the asymmetry of this guy, which you can prove it's a strict order, okay? So once you have 8, 9 is pretty straightforward. And I think once you have that in place, I don't think, for example, the assumption that the determination relation leaves holds between things at different levels. I would just get it for free, but I'm still, polishing the paper up. So now, this is supposed to capture the following thing. So this is my pride. Actually, it took me 4 hours to do this drawing in tech. It's just, so this is supposed to structure this structure, right? So you have one top level, you have the bottom level, you have only one thing at the top level, okay? And then you have different levels of determination in between, okay? So I also had color, but so in the case of color, there might be only 3. So you will have color here, you will have red here, and you will have maroon, crimson, and scarlet here. And you will have green here, no, green, I don't know, blue, and then you will have sapphire, pervincule, and ultraviolet, or whatever you have. Okay, now, note the following thing, that given my assumption, it is gonna, let's move on, and I will tell you why. I will tell you something about the notation that I used. So as of now, I think I hope that I captured that with the formal construction I gave. Yes, Bruno.
Sorry, Claudio, this is just for clarification. So can't you have, for instance, DJ1 also seeing the K bottom? So basically, so in the beginning, you told us about these principles that govern determination. So what did you call them? Requisite determination and unique determination. But you're not assuming them, if I understood correctly. So the question is whether you can have 2 determinables that share determinate. Because that does not seem to be prevented by a strict order. Sorry.
You see, you see, I'm getting old, right? That's what. No, you're completely right. Meaning like that, as far as I can see, nothing in the construction I gave prevent that. It is a principle, as a matter of fact, usually in the determinable determinate literature, as a matter of fact. So, but as far as you can see, you're completely right. Nothing I said prevents that. Good. So I'm gonna write it down, because that's important, as a matter of fact. Not for the rest. We will see some axioms, but you're completely right. At least as far as I can see, you're right.
Just to say that if that's right, then you might have troubles getting 8 from 6. But yeah, let's talk about it later.
Yeah, no, you're right. You're right. You're completely right. Meaning like, so the argument actually depends crucially on that. And I don't think
I think so.
Yes, no, yeah, the argument, if I think about it in a minute, the arguments actually depends from that. So I should actually impose it, given that my construction, as far as I can see, I'm not able to get it for free. So I will actually impose it, because this is a usual. So you will see that there's another one which I will impose, which is, so the one that I will impose are not generally contested in the literature. But of course, this is philosophy, right? As soon as you have an axiom, there's going to be one. This is recorded. I can't say axiom, right? Well, I just said that. So I just said that. So there's going to be someone that says, of course, there's violation of counterexamples to that, right? So as far as I could see, this one is everyone across the board holds it, but you're completely right. Thanks. That's a very good point. Sharing. Sorry, guys, because this is important. Okay, good. So now, keep in mind what Bruno said, which I think is completely right. And if I don't get that, then I don't get to say the things I'm going to say, right? Because the thing I'm going to say are meant to be cast against the background of the construction I gave. So I think that Bruno is exactly right. So keep that in mind, and just believe, just think that I actually assumed it. I knew it before, and I just assumed it. Okay, good. Thank you. So against this background, right? So what I'm gonna do is that I'm gonna give you formal rendition of the principles we're interested in. Now, apart from the fact that I like to toy with formal things, it's just like it seems playful to me. I think that some, let's say, some subtleties that you can see with the formal rendition, you might not see without the formal rendition. And that's not that's not always the case, but sometimes it is. Let's put it this way. Especially for a non-native speaker and of English, I'm gonna tell you one little anecdote about that because of this. Now, against this background, right? If you actually pay crucial attention at intermediate levels of determination, right? You can actually ask yourself, well, take any axiom in the theory, take any axiom or any principle that governs the relation of determination. You can actually provide different variants of it, whether you relativize that to different levels. Right? What I will be interested in is what I will call unrestricted versions, okay, or unrestricted versions. But there are many more, and in the paper I make a lot of fuss about, well, beside the completely restricted one, the mildly restricted ones always entail the general one, and therefore I'm just going to work with that. So here's two examples. The first one is requisite determination, that if you remember intuitively says, oh, if you have a determinable, you have a determinate, okay? So the first one is the, let's say, unrestricted one. It says, if you have a determinable, you have a determinate for every level, okay? Now, if you look at this, I didn't put here that this guy here is a determinate of that guy. Should I put it? Well, it just so happens that my assumption, my controversial assumption, that there is only one at the top level, guarantees that guarantees by what I'm gonna say in a minute, that every other property in the family is gonna be related by D to the top guy. So that's why I don't have it. When I have the antecedent that has that in the antecedent, I don't have the conjunct D top, D other. When I don't have that, like this here, so I have to put the conjunct, okay? Because I'm not guaranteed, for example, right? So it might very well be, fish out green here and fish out maroon here, which is not a determinant of green, it's a determinant of red. Now, but all now it matters. This is just to simplify notation here, because I'm still having trouble in doing multi-line equations in LaTeX. So the only thing that matters here, right, is the following. You can see immediately, right, that 10 entails 11, but the converse does not hold. 11 just says, oh, if you have a determinable, right, you have a determinate at the bottom level. It doesn't say anything of things in between. It just says, oh, if you're colored, you're going to be, let's say, scarlet. It doesn't say anything about whether you have the one in between, green, red, blah, blah, blah. Now, by this construction alone, 10 entails 11, but nothing guarantees that 11 entails 10. Now, to be honest, there is a principle in the literature which is called determinable inheritance, which is exactly like the other principle that Bruno mentioned, that everyone that I know of endorsed this principle, so I will do the same. And the principle tells you that if you have a determinate, you have a determinable. So you can always go up. The problem is going down, is going to the more specific ones, you will see, with metaphysical indeterminacy, but you can always go up. So if you are scarlet, you are red, and if you are red, you're colored. Okay. Now, if you have that, which is this one here, okay, then 11 entails 10. And the two are materially equivalent. Okay. Why? Roughly, why? Because suppose you have the antecedent of 11, right? Suppose you have the antecedent of 11, what this tells you is that for every level up to the top, right, you will have a determinable of that, which is going to entail exactly this. It's going to entail the consequent of 10. Given that the antecedent is the same, in the presence of the I, these two are materially equivalent. Why am I saying this? Why am I making a lot of fuss? Because you will see the other principle of determination that we really look at, unique determination, that's not the case. There is no bridge principle that gets you. I mean, there is one bridge principle, but the bridge principle is this guy, requisite determination, which is problematic. And I'm going to show you that's the next move. Okay. So here's the literal translation of the uniqueness requirement. Remember, the uniqueness requirement goes, oh, if you have a determinable, you have a unique determinate of that determinable. That is, if you have the determinable color, you only have red. You're either, let's say, red or blue. And if you have red, you only are scarlet or crimson or whatever. Okay. Now, so this is, for example, where, I mean, even if I'm speaking English for a long time, I still haven't, I still couldn't see the difference in the English formulation. Now, this translates the following formulation here, which is only the restricted one because I'm interested in that. It's a literal translation of the uniqueness requirement. Look at this. It says, well, if you have the determinable at the top level, you have a maximally precise determinate and only one. You have one. That's the first conjunct says you have one, right? And the second conjunct, basically it says, oh, and you have a unique one, right? That's just. Now, there is a weaker requirement, which I've been told I didn't have to actually do it formally. You could hear that in the English formulation. I couldn't, for example, which is at most one. It says if X is a determinable di, it has at most one determinate. Okay. Now the formulation is the following, and it's crucial now that I give you the unrestricted one, which says, well, if you have a determinable, you're going to have, you have at most one determinate for every level. And this one is the restricted version that says, if you have a determinable, you have at most one maximally specific determinate. That is the one at the bottom. Okay. So this doesn't translate the unique determinate. It translates actually at most one. So I clearly see the difference formally, right? So for example, you could see formally it's clear that this guy entails this guy, but the converse does not hold, right? And this will be crucial. We will see why. Okay, but I couldn't see it at first. Why in the English formulation? I've been told that there is a way which is unique and at most one. Even in English, they should sound different, and this one should translate the at most one determinate, and this one should translate the unique determinate. Okay, but once you have the formal rendition, it's pretty clear. This guy entails this guy. I'm sorry, it entails this guy. This guy does not entail that guy. The same thing goes here, right? So you can see that's the same dialectic we have here. So this guy entails this guy by logic alone, and the entailment between this guy and this guy, right, was supported by this principle of determination, which we will. Now, you can ask the same thing here. So clearly this one entails this one, right? This is just by logic alone. Does this guy entails this guy? And the answer is no, right? There's nothing in the logic that actually makes you infer this one from this. Is there a principle that can bridge that? Yes, it's this guy. Requisite determination will actually make these two equivalent, materially equivalent. And this is important. We will see why, because cases of metaphysical indeterminacy actually violate this guy. And if they violate this guy, now the distinction becomes crucial. Okay, or at least that's what I'm about to argue. Good. So if I'm right, if I'm right, and if you don't have this, right, and these two are different, you might have different violations, let's say, well, different violations. So something violates one principle, but it doesn't violate another. So here's an example which we'll return to a little bit later on in the lecture. And I'm going to do something that a lecturer should, someone that gives a talk should never do. I'm going to ask you a question because I honestly don't know the answer to this. So the logic alone, if you don't have requisite determination, these two will not be materially equivalent, okay? This one will entail this, but this one will not entail this. These open up the following possibility. Something that has a unique determinate, okay? So it has the determinable at the top level, like color, for example, right? A unique determinate at the bottom level, scarlet, let's say, right? But no unique determinate in between. At least as far as the logic goes, this is logically possible. And I couldn't come up with any example of this, as a matter of fact. I might have some thoughts, but we will see a little bit later on more. So let me go over. So now this is the construction that I will use, right? And you already saw that once you have like different levels of determination in between, things gets a little bit more complicated. And now you can play along with restricted and non-restricted versions of the axiom. And then it's a crucial question, which one entails which? And for some entailments, logic alone will do the job. And some entailment, to get to the entailments, you get other principles in the theory of determination, in the logic of determination, some principles that you might want to give up. And that's exactly what we're going to see over now. So here, just to foreshadow what we're going to see. So the entailment from 15 to 14 is guaranteed by requisite determination. But I'm going to argue that, well, that's pretty easy to argue, that cases of metaphysical indeterminacy violate requisite determination. So, and here's, so let's move on to these cases of metaphysical indeterminacy. Oh, by the way, this is not the type of talk in which I defend the determinable based account. I defended it for quantum indeterminacy, for just the indeterminacy that comes from quantum mechanics. But I'm not willing to actually say that it can handle everything else. It seems to me that quantum mechanics is a good example, because I can immediately, I can see how to, characterize objects in quantum theory to, determinables and determinates. For some other, I don't see that clearly. For example, in the case of the open future, I don't see what determinable determinate structure there is there. And this is just to say, I'm not defending it here. I'm just exploring the consequences. And here, what Jessica says. This is the quote from Jessica. These two different papers. So let's take the first one. It just says, well, what I said at the beginning, right? What it is for the state of affairs to be metaphysically indeterminate is to involve an object such that it has a determinable P, and for some level, this is a point for some level, does not have a unique determinant of that. Now, if you look at this here, talk about for some level actually vanished. And she says she's clear that this is a simplified version of that, because she was writing for a book here. Now, I take it that, and I talked to her, she confirmed that this is a simpler formulation, just because it doesn't pay attention, because it was not important for what she was doing in the paper, to different levels of determination. But now, of course, if you do pay attention, right, you can distinguish between the following cases. Unrestricted metaphysical indeterminacy acts as a case of unrestricted metaphysical indeterminacy if and only if it has a determinable at one level Li, and then for all levels that are more specific than that, it lacks a unique. Then you have restricted to the bottom, in which you say, oh, if it has a determinable, well, it lacks a unique maximally precise determinant, that is a determinant at the bottom level. And then you have restricted MI, which says that X is a case of restricted MI if it has a determinable, and there is one level such that it fails to have a unique determinant there. And I put it in this order because, as far as I can see, all, oh yes, I put it there, all the downstream entailment goes through. So these entails this, but none by themselves of the upstream entailment goes through. Okay. So if this is correct, which is a big if, cases of unrestricted, restricted, and restricted to the bottom cases of metaphysical indeterminacy might violate very, very different principles of determination. Here's one we already briefly discussed. A case of restricted MI, remember the restricted MI is a case in which you have a determinable and there is one unique, there's one level, which it doesn't have to be the bottom level. There's one level at which you lack one determinate of that. Okay, you lack a unique determinant of that. Now, might not violate, for example, at most one determinant when it's restricted to the bottom level, right? Because it might be the case that X is a unique maximally determinate at the bottom level and does not have, for some level, a unique determinable at that level. Now, I think that this is just, so here's the question that I wanted to ask. This is just a logical possibility, meaning by logical possibility, something very rough like, oh, as far as this construction that I gave you about the logic of determination, this is compatible with that logic. Nothing in the logic of determination rules out this case. Now, that doesn't mean that any such case is metaphysically significant or I actually can think of one. As a matter of fact, I can't. So if you have any idea, I would be super happy. Of course, I will mention you in the paper. I mean, just it would be a very, very small, so like, font like 8 or 7. So if you can think of any such, I couldn't. So the only thing I could think about, if there is such a case, which I think it's interesting, if there is such a case, it will be a case of glati, ME. That is, it will be a case in which you have a determinable, you have a unique determinate at the bottom level, and you have more than one. It cannot be a case of gapping. And we will see it more later on in more detail, but here the thought is the following. If you have a determinate at the bottom level, right, now determinable inheritance, which is the principle I assume that says, oh, if you have a determinate, you have a determinable, guarantees that you have at least one determinable of that, which rules out gapping. So here's a logical possibility, which I think okay, I've been told that I should never use cool in a philosophy talk. It's a significant possibility, logical possibility. Amanda agrees, right, that I should, no? Okay. No, no, because it was not there. So there's this guy, Kevin Mulligan, this famous guy that says, you should be actually, thrown out of academia if you say cool and I did it. So, but the thing is, so what strikes me as interesting is that the logic by itself tells you that this is a possible case, and the logic will tell you also which case it is, because it will rule out the logic of determination that it's going to be a gappy case.
Claudio?
Yes.
Sorry. Can you please, if you can reframe the problem like for non-logical experts like me to understand what you're looking for in this case? Because I don't know if I got this right,
Yeah, so I mean, I'm no logical expert either, so I'm happy actually to see it. So I like to toy with this, and I usually am mistaken most of the time. I told you, like, the first thing that I did, I sent it to a mathematician and says, that's not a strict order. So, I mean, clearly it's not, logic is not. So here's the case I'm thinking about. And here's what I could come up with. But that's a very bad example. So the case is that a case in which you have a determinable, let's say the maximally unspecific one, let's say color or heavy mass. You have a unique determinate, maximally specific, the one at the bottom, okay? But you have no unique one in between. So in the case of color, it will be crazy. It will tell you, oh, you are colored, you are scarlet, but you're not really just red.
Okay. Well, okay. Yeah, okay. So maybe I'm thinking there is a paper by David Wallace.
Let me just, sorry, I'm really sorry. Let me just point out to people who are making interruptions. It's fine, but keep them to an absolute minimum because we are recording the session. So you're going to be on the video. That
right. Thanks, Dave.
If it's a clarification, by all means make it. But if it's a question or a point, let's keep it.
Let's discuss in the Q&A session then.
Cool. Thank you.
Okay. Thank you, David.
Yeah, because when David Wallace's name pops up, it's never a clarificatory question. It's never. It's not going to. So here's what I thought, but I've been convinced by Jessica herself, that it's a bad case. Mass, let's say mass is so you have a mass. I'm unfortunately in the pandemic, I'm 96.7 kilograms. So I have a unique determinant of that. But now, of course, it seems that I have the following two determinables intermediate level, or being between 95 and 101, and being between 97 and 102. So in this case, right, it seems I have both those. But of course, I mean, here the challenge is that, well, but these are not really determinants. Mass has just two levels, mass and the determinant values. So I could not think of any, actually, as a matter of fact. But I will be super happy if you guys have an example about that. By the way, I should be upfront and say, like, because, and I think she's right, Jessica insists on that. So we actually explored Glatti and Guppy cases in quantum mechanics, orthodox quantum mechanics, relational quantum mechanics, a bunch of interpretations. And I don't want you to think that the people that endorse Glatti cases think that something can be both red and green at the same time without just directly. Either usually are relative to different perspectives, and perspectives should not be constructed as another argument places, or to a degree. So I can be, so they would say, for example, that you can be 35% green and 65% red, but they will not say that you can be 100% red and 100% green, okay? Because these versions are inconsistent. So I will not mention this because it's just too long, but just keep in mind that. Okay, good. So now, once you have that, first of all, I'm going to show you I'm going to argue that there are some pretty significant consequences for the two versions of metaphysical determinable indeterminacy that have been frequently mentioned in the literature, Guppy and Glatti. And then I will move on to say, oh, there's a third one, okay? So first one is, Guppy, remember, acts as a determinable, but not unique, okay? Now, of course, you could distinguish unrestricted, restricted to the bottom, restricted cases. Just replace here, right? Instead of Laxa unique, just replace every time Laxa unique, just replace it has none, okay? So you will have unrestricted, Guppy, restricted. So now the question becomes, which principles of determination they violate? Well, we argue that these two guys, which are clearly violated by this, because requisite determination says, oh, if you have a determinable, you have a determinate. So clearly these cases will violate that, right? Will they violate, is going to be a difference between the restricted and the unrestricted version? No, because they're materially equivalent. So if it violates one, it violates the other. Okay. This is not the case, though. That's an important thing. That's crucially not the same thing for unique determination, as a matter of fact. We will see it. But here's before we move that, before we move to unique determination and Glatti, here's a question: does Guppy violate unique determination? And here's an informal argument you might have. Well, in restricted Guppy cases, you can use just restricted because it's easier. Some object has no determinate at the bottom level. A fortiori, it does not have a unique determinate at the bottom level. And this simply is a violation of unrestricted unique determination. Now, the formal counterpart to such an argument is based this is very trivial. It's just, well, this guy entails this guy, right? I know that you don't remember, but believe me when I say this guy is just the conjunction of this guy and another thing. So of course it entails this. And given the Guppy cases violate this, of course they're going to violate unique determination. Now, the point is that, though, I remember that I distinguished another version, another principle in the ballpark, which was at most one. It was not unique one, it was at most one. Does it violate that? And the answer is no, right? Because, for example, if you have a case in which, for example, restricted to the bottom, in which you have a determinable, let's say you're red, but you're not any specific shade of red, these will trivially satisfy at most one determination. Because at most one determination, if you think about it, it says, oh, if you have one, then you have at most one. So if you don't have one, it's trivially satisfying. And the formalization actually gives you that immediately. Unique determination entails requisite determination, which is the principle violated by Guppy, but at most one determination does not, as a matter of fact, entail that. Naturally enough, right, this guy and this guy we saw are material equivalent in the presence of the requisite determination. But this is not something you can appeal to when discussing GAPI cases, because GAPI cases are exactly the ones in which requisite determination is violated. So, and this actually is crucial to dispel an objection that Jessica raised to me, which is a very good point, as a very fair point, I think. Here's the objection. Oh, you're just making your own rules. Right? So this guy at most one determination was never part and parcel of the logic of determination. If you had read the original papers on that, you would have seen that what they really mean is unique determination. Right? No one actually thought about yours. So it's unclear why I should even care about this, unless we're given independent philosophical motivations. Now, I think I have independent motivations that comes from another area of philosophy, which I'm working in. I'm trying to write a book here with Fabrice on theories of location, but it will take us away here. So, but here's what I think, what I can say in this setting. Given requisite determination, these two guys are materially equivalent. One entails each other, okay? This entails this and this entails this. So there's really little interest in distinguishing them. And as a matter of fact, almost everyone that wrote in the determinable literature endorsed requisite determination. Now, my point would be exactly in the cases in which this guy is violated, as in GAPI cases, that provide motivations for distinguishing them. Because it is exactly in those cases that they're not equivalent anymore. Okay, so that unique determination entails at most one determination, but at most one determination does not entail unique determination. And therefore, in these cases, perhaps there's there's space to argue, and I'm curious to see what you think about this, that the uniqueness, the at most one requirement in these cases can do the job of at most one requirement can do the job of unique requirement, because at least it says, well, if you have one, right, then you have only one. But it leaves open whether you have one in the first place. And unique determination, on the other hand, doesn't leave it open. It says that you have. Okay, good. So I think that this is important, and here's where I disagree with Jessica. So what about GLATI cases? Well, the GLATI case is a little bit more interesting, right? Why? Because so remember that it says it has a determinable and more than one determinate, either relativized somehow or to a degree less than one. So I think that Smith and Rosen has something like this, for example, and Smith has an entire book on degrees and determination. But this is more interesting because, of course, you can still distinguish between restricted to the bottom and restricted cases. But in this case, the target principles of determination that they're supposed to violate, unique determination and at most one determination, in all of the versions are not equivalent. Unless, of course, you require requisite determination. So if they're not equivalent, it's a substantive question, which cases violate which version of which principle. And so I'm going to go quick. So, right? How I am on time, Amanda?
Well, if you wrap up in the next 5 or 10 minutes, that'd be ideal,
so
but we're not going to be too strict about it.
I'm going to go fast. So let me point out. Okay, so you will have a distinction here, and what I want to say is coming back to this case, right? The case of restricted GLATI-ME, which is the one we'll be discussing a lot. This one will be a case in which you will have a determinable more than one determinate. One determinate at bottom level, but more than one at some level. This will violate the unrestricted version, because the unrestricted version tells you that at every level you have one, but it will not violate the ones at the bottom. Now, and this points to a crucial difference between GAPI and GLATI. First of all, GAPI and GLATI, right? Well, of course, they violate different principles, but within the family of principles that they violate, GAPI violates all of them, the restricted and unrestricted version, because just is material equivalent. GLATI is not that like this. It can violate some of them, okay? And as one case will be exactly the case that we've been discussing for quite a few minutes now, right? the case in which you have a unique determinate at the bottom, more than one at the intermediate level, and one determinable here. And as I said, there is no gappy counterpart to it, right? So you cannot have y, and now we can see the argument a little bit better. Suppose that is the case, right? So by deductive, suppose that you have a determinate here and you want to say, well, there's some level at which you don't have any determinable. Is it possible? No, right? Because determinable inheritance would say, oh, if you have one here, you will have one here, and you will have one here, and you will have one here, which will actually contradicts the assumption that it is gappy. Now, if you think about it a little bit, what it tells you is that here's a crucial difference between gappy and glati. Gappy is the version of trickle-down economics. Gappy, once you're gappy, the gappiness trickles down all the way to the bottom. If you're gappy at a level, then you're gappy all the levels that are more specific than it. Whereas that's not the case for glati. Glati can be contained. Okay, so that's a crucial difference, and it will help me actually pass to the next to the next and concluding section in 3 seconds. So as we saw, right, there's already a significant, I would say, significant consequences if you have intermediate levels of determination just for gappy and glati, which are the ones that that have been mostly discussed in the literature. Now I'm gonna say that if and the next step is say, well, there's a third way for something to be MI. Because of course, if you restrict to one level, you're either gappy or glati, right? But nothing forbids, right, in the logic, if you have more than 2 levels, or if you have one level, if you have just 2 levels, the top and the bottom, then you cannot get this. But if you have even just one more, what can happen is that you can be gappy at one level and glati at another. And I'm gonna say that I'm gonna define this as glappy. Here's the first definition. Glappy is a case if it has a determinable, okay? And for some levels, Lj and Lk, such that they stand in this relation, okay? So the Lk level is the more specific, then you have Lj in between, and you have Li. X is more than one determinate at Lj, the one in between, and no determinate at these guys. So it has this determinable, it has more than one here, and it has only one here. And it has none here, okay? Or here's a provably equivalent definition. Say that something is glati at a level Lj, okay? If it has a determinable at a less specific level, okay? And more than one, somehow more than one determinate at that level Lj. Do the same thing for gappy. You have a determinable, and then at one level down, more specific, you have no determinate, okay? Now you have a case of glati, and these two definitions are provably equivalent. I hope I did it correctly. So you have a case of glappy when X is glati at a level, gappy at that level, and another level, and the level at which it is gappy is more specific than the level at which it is glati. And the argument is still the same, right? In the presence of the I, that's the only possibility you have, okay? Because gappiness in the presence of the I will trickle down all at the bottom. So you cannot have something that is gappy here, but glati here. You will have to have, if there is such a thing as glappy, it's gonna have to be the reverse. Okay, so once again, this is just the argument I gave. In both characterization, if you can see, right, which I said here, you can see that in both characterization, I say that it's glati at a more specific level. As a matter of fact, this clause is redundant. Like you can prove that that's the case. Okay, because gappiness trickles down. Now the question will be the parallel question to the one that we have for the cases we just talked about, right? So this is a logical possibility, namely in a very broad sense. Like the logic of determination doesn't exclude glappy cases. Now, is there any example of that? Now, I hope the quantum mechanics will give me one. So, and here's my convoluted example about quantum mechanics with a special eye to Davide here. So I'm not, by the way, to be crystal clear, I'm not endorsing this thing. It's just a very convoluted example to see to show how it works. As a matter of fact, I don't think that this is a good characterization of spin. That's what I'm going to use. And I know that some familiarity with quantum mechanics is assumed, but just look at the pictures. If you're not, so the spin is just a property. Let's say it's a property of quantum system. Let's put it this way. Okay, and it's a property that you can have relative to directions in a particular space, which is called the Hilbert space, which is a space associated with a quantum system. Suppose and these guys are usually represented mathematically by operators, by emission operators. I mean, in the quantum mechanics 101, like just in the very, very basic introductions. So you can have a spin operator for a general spin in the general alpha direction for the Hilbert space. Now, you might be familiar, at least for reading some literature about particular ones of this, like the so-called Pauli matrices for spin in the X, Y, and Z direction, which are the ones here. Okay, these are examples of this. It's not difficult to see that these are examples of these, right? So if you want Sx, right, just attribute 1 to X and 0 to Z and Y, and you will see that you get this. The same thing goes here. So if you want Sy, just put X equals 0, Z equals 0, and Y equals 1, and you will see that you get this matrix here. The same thing for Z. Okay. Now, these things can only have two values for a spin half particles, let's say, for electrons, let's say. They can have only value +1/2 or -1/2. So here's how the first step that you have to take. Argue, I don't know how, don't ask me how, I honestly don't know. Argue that this guy here, Sx, is a determinate of this. And then argue that +1/2 and -1/2 are determinate of this. This is the last part is common in quantum mechanics literature. So there's Alisa Bokulic that defends the view, Joanna Wolf that defends the view, Jessica Wilson herself that defends the view. It's implicit in some classic about, so for example, Hugh's Introduction to Quantum Mechanics, Peter Lewis, for example, holds the view, and so on and so forth. The very controversial claim is that this guy is a determinant of this. Pictorially, and this is my another pride, is that suppose that spin has this determination structure. You have S alpha here, you have Sx, Sy, and Z. Well, actually, you should have uncountably many here. And then you have the maximally determinate values here. So suppose you can argue that this is the structure of spin. And now take a quantum system in this state. Now, it doesn't matter. Just believe me when I say these things are not, I will tell you when they are when I'm saying controversial things. Suppose you are in this state. This state is called an Eigen state of this operator here, which belongs to the eigenvalue +1/2. It just says that when you have an electron in the system and you measure spin, you will always find with certainty that it has spin x +1/2. Okay. So now, if this is the case, by the logic of determination, you can argue that it will be here, so it will have this property, right? By just the principle of determination, you can argue by determinable inheritance that it has this determinable, it has Sx, and it also has S. Okay. What about the other guys? Now, if someone is smart enough to say that, well, if it has one of these, it has all of them. Like if it has one in one direction, it has at least the spin one for all of them. But given that, in jargon, a spin in different directions are incompatible properties, let's say that very roughly, like if you have one precise value of one, you cannot have a precise value of the other. So you cannot both have precise value for spin x and spin y. Suppose this is evidence enough to say, which I don't think it is, but to say that you have no value for spin y. Okay, then you will have a case of Glappy. Why? Because you will have so you will be the electron will be here. It will have this just by the logic. You just argue that it also has this. So at this level, it will have more than one. Somehow, mediatedly, whatever, okay? But we just argued also that at this level, at least for one property, right? So when you actually focus on this, right, it will have no value for spin y. So it would be glati here. So if you take that root, it would be glati here and grapi here. Okay, so, but this is the only principle, this is the only example that I could come up with. But I mean, it hinges on so many controversial assumptions that I don't feel actually comfortable with it. And it's not just controversial assumptions like what is known in the literature as, you know, the eigenvalue, eigenfunction link or whatever, that in the philosophy of physics is controversial, but in some other areas of philosophy is less. It really, really depends on crucial and very controversial assumptions about spin being, you know, this determination structure. So if you have other examples, please, once again, let me know. And with this, I think it's done. And before I leave, so remember, so there were cases of metaphysical indeterminacy, right? The solid case cases was one, indeterminate future was another, quantum indeterminate is one. The other one that is usually put in the literature is the one over many problem. So you have a cloud, right? And it's indeterminate whether there is one cloud, many clouds, and whether one cloud has one shape or another. And some people, so for example, Jessica wants to actually apply the determinable based account also to boundaries, vague boundaries of macro objects, such as clouds. And, you know, to leave you, it's just one of the most beautiful passages from Shakespeare. So no metaphysician has gone even close to the beautiful passage here. So that means that all the work we've done, it's not worth a line in this scene by Antony and Cleopatra. So this is almost immediately before Antony dies. So, and this is just the, so it's immediately after Antony actually basically said to Cleopatra, okay, yeah, so he's winning the war, but then Cleopatra leaves, you know, goes back to Egypt. And Antony goes, oh, I'll choose love over the Roman Empire. And he follows her. And then, you know, the fleet got destroyed. And then they, you know, they stand here and they clearly see, so they look at this, they look at the clouds and they clearly see, oh, maybe I've done something bad. Like, you know, these are going to be black signs at the horizon. And of course, it will die in 2 scenes. So, and that's it. So that's it. Thank you so much.
Great. Thank you very much, Claudio.